Hi, and welcome to Lesson 1.3 of AP Statistics, where we'll wrap up Chapter 1. I realize Chapter 1 is rather direct and easy, and don't be fooled because the AP questions aren't always as straightforward as you think they should be. Some people do great on the first test. Some people that understand the material do strangely on the first test because they're not accustomed to the type questions. So please use the practice test posted in the class website and do all the homework questions with an eye toward making sure that if things are asked in a confusing manner that you get answers to your questions. All right, let's proceed. So long list of things here. It's still not going to be that long a video, but want to point out some things. Instructions on AP test questions are very specific in the types of verbs that they use. Calculate, you got to show your work or show how you got it on the computer. I'll always talk about what you have to show when you do that. The word interpret is very specific. It means that there's a set wording that you can memorize and use every time. And we'll add to our list of basically scripted interpretations that you can just use without having to alter them, except to put in question context. Identify, make, interpret, use. So we'll make sure we pay attention to these words as we go through the section so that you learn the proper form of answering questions. Now I'm going to say mean is probably easy enough that you don't have to show the formula when you do it, or put in a calculator command. So there are things that you can do by hand and that you can also do in the calculator, and sometimes there's calculator commands you have to show when you handwrite your work on FRQs, and sometimes there's not. For mean, you would not need. You just need to put X bar and put the number and go on. So X bar is the mean of a sample set of data. If you want to talk about the mean of an entire population, that's going to be the Greek lowercase letter mu, which we haven't used yet. So when we get there, I'll point that out to you again. I'm going to make sure I talk about Greek letters and how they're used. So you've used the capital sigma symbol before in probably analysis or honors pre-cal, where it's the summation symbol telling you to add up a bunch of terms. And so when you see this formula down here with the summation of x sub I, well, the I would be a subscript, so that x sub 1, x sub 2, x sub 3 are represented by different data points all the way up to the nth data point in a data set. So the subscript just indicates every individual data point in a set. Notice they're not so formal as to say I equals 1 to n like they would in algebra class. It's just an understood shorthand. Then dividing by the number of items in the set is the traditional definition of an average that you've learned before, but we don't say the word average in this class. We say the word mean, and you can also say X bar when you mean the mean of a sample set of data. Alrighty, we also have a lowercase sigma, and we'll talk about that when we get to standard deviation. Median. We've talked about how to do median, or you've talked about how to do median in the past. It probably was middle school math or even younger. So just follow the instructions here. There's instructions if there's an even number of data points or an odd number of data points. Make sure that you understand what to do when there's an even number of data points, just averaging the two middle values together. So that the median doesn't necessarily have to be a data point in the data set. So we'll see how they handle that here. 20 randomly selected New York workers gave their commute times to work. And we notice that there are in 20, that's not an odd number. So when we go to find the median, they did a little quickie dot plot here, and they counted up the 10th and 11th data points are 2, 0, and 2, 5. Make sure you read the stem plot correctly. So they took the average of 20 and 25 to get the median. When there's an odd number of data points, then you don't have to average two numbers together. There is a specific middle number. So watch that you're taking care to do that calculation properly. And then we'll slow down a little bit here for interquartile range. So the quartiles, the prefix of this word is quarter, quart for quarter. So these are the numbers that split the data set into quarters. So Q1 is not the minimum value, but the value that separates the first 25% of the data from the second 25% of the data. The median separates the second 25% of the data from the third 25% of the data. And Q3 separates the third and fourth quarters of the data. So if you will, the first quartile, I like the way they define it here. Q1 is the median of the observations located to the left of the median in the ordered list. So when you have an ordered list data set, you put all the data points in order and you count, you find the median of the entire data set. Then you look at the items to the left of that median, and Q1 is going to be the median of just the left half. And then on the right side, Q3 is the median of the data to the right of the median in that list. So I like finding it that way. They will only ask you to do this in data sets that are small enough to do this quickly. And it's a very handy way to identify quartiles. Technically speaking, Q1 is roughly equivalent to the 25th percentile of the data, which we haven't officially defined yet, but if you remember what that means, then you associate the first quartile with our Q1 with the 25th percentile. Median is, of course, the 50th percentile, and Q3 is the 75th percentile of the data set. And so when we get to percentiles, we'll go over that more closely. But the difference between Q3 and Q1 will give you the width, the range of the middle 50% of the data. So I really like to show you a box plot to identify these things with. And so they walk you through this nice problem finding the median, which they already found in an earlier setting. Now we find just to the left of the median, we've got 10 data sets. So the fifth and the sixth one, the average of those two is 15. And the 10 data points to the right of the median, the fifth and sixth items average together and you get Q3. And so the interquartile range is the difference of those two numbers. And that's the width of the middle half of the data. Now, these two numbers right here, 15 and 42.5, Q1 and Q3, I'll give you an example of how you've seen those in real life. Now, I know all of you have filled out college applications, and you've looked at schools' published ACT and SAT scores for their freshman classes online, and they'll show you that they have a range of, whatever the two numbers are that they give you, and they're giving you Q1 and Q3. They're not giving you their lowest score and their highest score. They're giving you the middle 50% of the current freshman class. So you'll never know what the min and max are, and they will not publish it, mostly because they don't want to intimidate people into not applying or brag too much. They want to brag a little, but not too much. They're not going to give you their max scores either. So I will say that oftentimes scholarship athletes bring their scores down, and so that's why they don't like to publish their minimums. Not all athletes bring their scores down, but some of them do, and they don't want to publish those minimum scores. They can also be sued if they state definitively that they will only accept students with scores between two numbers. So they're pretty vague about how they present those numbers in real life anyway. Okay, so you would say the interpretation. Now remember I said interpretation means this is stock wording that you can use whenever you have to interpret what IQR means, if you're instructed to do that in a question. So the range of the middle half of travel times for the New Yorkers in the sample is 27.5 minutes. So the travel times and New Yorkers, those two would be part of the context. Putting minutes, putting units on the measure, 27.5. Essential, and that's the context of the question. So you can kind of think of or take notes and say range. The range is the middle half of blank for blank in the sample is blank. You can put in the context yourself, but you could borrow this wording every single time. All right. Okay. So this number, the IQR, gives you an official rule for finding outliers and saying definitively that a number is an outlier. When you're given specific data values to work with. You have to be given data set to calculate this. Otherwise, you're just stating that you think something is an outlier because it falls outside the established pattern of data. With this rule and with an actual complete data set presented to you, they would expect you to calculate it and know for certain whether a number is an outlier because we can't always eyeball it. So for this same data set we use, they are identifying Q1 and Q3, and they got the IQR from that of 27.5 minutes. And here's your rule. 1.5 times Your interquartile range is the first number you calculate using IQR. In this case, we get 41.25. So we're going to go to Q1 and Q3 and think of them on a number line. Q1 is the lower one, and we'll subtract that 41.25 from it and get a lower value of negative 26. We will add 1.5 times IQR to Q3 and get an upper value. Now this lower and upper value is the range of usual values, things that are not outliers. Anything outside of that range would be considered an outlier. And it's okay that this went negative. It just means there can't be outliers on the lower end when commute times have to be positive numbers, but there might be some data where negative numbers are relevant. So here we know that we have a data point of 85 in our stem plot of the data. We've got our data point down here at the bottom. That would be outside of this range, so we could officially say that 85-minute drive to work is an official outlier in this data set. Okay, so to continue using Q1 and Q3, the 5-number summary can be, for a data set, can be calculated if you enter the data into a list and you go to the one variable statistics the videos that I've put in your calculator stuff section does cover how to come up with the 5-number summary, but it's more than just the 5 numbers, it's the one variable statistics. So go look for that video. And if you need to ask questions about how to use the calculator in class, I'm always open to that. But you can almost always find good videos on YouTube if you just put TI-84 and then put what you want to learn how to do. They'll come up with dozens and dozens of very excellent, short and to-the-point videos on how to use your calculator. This is for efficient use of time on an AP test, that you learn how to use this calculator extremely well. And when there's a manual way to do something, just know that it's always going to take longer than doing it on the calculator. So I recommend that you become very good at the calculator so that you can maximize your use of time on the AP exam and on chapter tests. So the 5-number summary includes the minimum Q1, the median, which some texts and questions also call Q2, Q3, and the maximum value. And we put them in a box plot. So you can look at the steps of how to make a box plot here, take notes from it however you like. If you've already taken reading notes, that's even better. But let's look at how to put this box plot together. So we put in all of these elements. The box is the interquartile range, and you can always go down here on the scale. Just like a dot plot, we only have a horizontal scale, and we must put a label. We must put regular intervals, and so we can come over here. The left end of the box looks like it's sitting at 15, and indeed it is. The right end of the box is sitting halfway between 40 and 45, and there it is at 42.5. So we can get the IQR off of the box plot. These lines coming off the side are the whiskers, and they show us min and max. But, I mean, obviously our max was way up here at 85, and they could have chosen to extend this line all the way out to 85. However, they opted to put a symbol at this outlier. Since we determined that 85 was an official outlier, they put a symbol there, and then they only extended the whisker to the next highest value. So you can see the gap between that value. Your calculator, your Texas Instruments calculator, will do 2 different kinds of statistical plots. If you hit second and y equals and go look at the options for statistical plots, I apologize for not showing you on the screen, but my calculator software for the computer has expired, and I'm waiting on a code for that. But if you'll hit the second key and you'll hit the y equals key, it'll bring up the statistical plots, and you can choose one or any one you like. And you'll see the types of statistical plots. You'll see the 4th and 5th plots are box and whisker plots. The 4th one will list outliers. It will calculate it for you and show you when you have outliers. So for that reason, I like to use that one more than the other one when I am trying to get a sense of data. When I've been asked to draw a dot plot, or excuse me, a box and whisker plot in an FRQ, I use my calculator so that I don't have to do any of the number summary stuff by hand. I will find you a video of how to do box plots with the calculator and post that in the calculator stuff for you. All right, moving on. So, standard deviation. I believe there's one homework question where you have to do this by hand one time, and the rest of the time you can use the one variable statistics to do so, like is shown in the video. Here, this presentation walks you through all of the steps, and you need to understand what standard deviation is. There will be an interpretation for you that you can borrow wording, but if you don't know what it means, then a lot of stuff in this class is going to be difficult to understand. So let's walk through it one time and see what each step of the process is. So you don't have to do a dot plot just to calculate standard deviation, but first you get the mean of the data, and then you take each individual data point and you subtract the mean from it. And so they calculated the mean of this set of data regarding numbers of pets is 5, and they take each individual data point and subtract 5 from it. Now notice that some of the data points end up negative and some end up positive. Here they are. And if they just added them all up, some of the positive errors would cancel out some of the negative errors. So what they do is they are going to square each deviation, okay, whether it's positive or negative, so it does come out all positive, and add them all together. And they're going to take an average. Now, they add all these up, they get 52, and then they divide by 9 minus 1. There were 9 data points, but they're dividing by 8. I want you to realize that this is actually a very specific choice. I always have students say, why don't they divide by 9? And I'm going to give you an unsatisfactory answer. The answer is there's a 30-page proof of why this is more accurate as a standard deviation measure. If you care to read it, I will happily email it to you. I found it. I read about 3 pages of it, decided I was going to take their word for it. Okay, this is used in every standard deviation course or every statistics course I've ever taken. Standard deviation is found by, quote, averaging and dividing by the number of data points minus 1. In Chapter 7, we will talk about it more specifically. We won't get into the 30-page proof, but we will talk about how it gives you a better measure to use a standard deviation than simply dividing by 1. All right, the number you get here is the variance, and then you take the square root of the variance and you get standard deviation. So, number of pets in a household, the average is 5. That's a lot of pets. The standard deviation is 2.55. So let's think about what this all meant. Each data point minus the mean. That's how far a data point falls from the mean. We averaged that together. We squared them, made them positive, added them together, and took the square root. We averaged it together. So standard deviation is the typical or mean distance from the mean of the data set. And so I've used the word mean twice here. So let me restate that. I am going to use the word average, so pardon me. The standard deviation is the average distance from the mean that a typical data point lies. Okay, so I don't like to use the word average, so I'll use the word typical. Standard deviation is the typical distance that a data point will lie from the mean. Okay, you're going to have to use that before that makes a whole lot of sense to you. And so standard deviation is a very common measure that we will use throughout the entire course. You'll figure out how to calculate the standard deviation for different sets of numbers different ways, and this is the primary way for a general set of data. Standard deviation squared is called variance. It's another measure of spread. It's not used as frequently in this course, but it is an equally valid measure of spread that is a squared quantity. So it does skew our judgment a little bit. They don't use it as much in this class as they do, as you will find in other statistics courses. You do have to know what it is and how to find it, but we will not be doing very much in the way of interpreting it. So here is the formula for variance. You put it under a square root sign and you get the formula for standard deviation, and the abbreviation is S sub x. Up here, S sub x squared is variance. And in your calculator, when you do a one variable summary, it's when you go to your statistics menu on your calculator, just hit the stat button and arrow right once to get the calculation button. And number 1 under it says 1 var stats, 1 variable statistics. This is where you find the standard deviation calculation. And in this class, we're going to use S sub x in the calculator instead of the lowercase sigma sub x. So the difference is one of those is calculated as n minus 1 for the divisor here when we take the mean, and the sigma sub x uses just plain n And some people even debate that, how Texas Instruments programmed their calculator. Just know that we're going to use S sub x on the one variable stat screen. Again, I apologize I can't show you the screen just now, but I will find a way to put some screenshots up on the website for you. Okay. Learn to do it in your calculator, and you won't have to do it more than once in the homework. All right. Now, we know how to find the center of data with either mean or standard deviation, and we know how to find the spread using things like range, interquartile range, and now standard deviation and variance. So we have multiple ways of describing the center and spread of a set of data. When should you use each one? Okay, so I love this little summary right here. When data is reasonably symmetric, mean and standard deviation are the ways to go, okay? Especially when they don't have outliers. Mean is yanked around by outliers. So if you have outliers in a data set, you probably don't want to use mean unless you have a good reason to. Mean and standard deviation tend to go together. Median and quartiles, or interquartile range, are better measures for data that is skewed, because when there is an outlying value and a big tail of skewed numbers in the distribution, median is resistant to being yanked around by outlying values, because it doesn't matter whether the max value is 10 or a million, the median is going to remain the median. Whereas a mean value is greatly pulled off the center of the data by a huge outlier, which you'd like to think you can just throw outliers out, but you can't. It's not ethical if they were legitimate measurements. So we'll talk about ethics issues in Chapter 4 briefly, and what people do that break the rules of statistical studies on an ethical level to get the results that they like, especially when outliers mess things up. All right. So describing a distribution with measures of center and spread are always a piece of the SOX description, shape, outlier, center, spread. But there is no replacement for a plot. A dot plot, a stem plot, a box and whisker plot, a histogram. One or any of them is always better than just a numerical description of a data set. Okay, so here's something specific to our text, but also specific to AP statistics exams written by the College Board. The people that write this book are very closely in touch with people that write and manage curriculum and tests for the College Board, and they often are involved in helping write questions for the AP exam and how to write rubrics to grade those questions. And so this 4-step process that's presented here is something I'm going to impose on you to use and require of you to use for a time. I will let you know when you can let it go. But in the meantime, when you're answering questions that have multiple parts and a process you must follow, leaving out one of these steps will often cost you points. Now, you don't have to put state, plan, do, and conclude written in your answer, but it'll help you think through the problem and help you to state the problem correctly and figure out what numbers and ideas and processes you have to use to answer the question, then to actually do the calculations and to draw a proper conclusion. And leaving any one of these steps out of a statistics problem or an FRQ will often be a good enough reason for them not to give you full credit. So I'm going to ask you to use this plan for answering FRQs and stick to it. All right, so we went over interpretations. For specifically, so far we've had range and standard deviation that have had specifically worded interpretations. If you have any questions about those, please make sure you ask in our live sync session. So at the end of each chapter, I'm going to list some specific AP exam tips from the appendix of your textbook that I find to be excellent guidelines and ways of helping you not miss points that are easy to get just because you're overlooking something simple. So I may have said one or all of these during the course of my lectures, but this is just to reiterate them. When you compare two sets of data, you must not just list shape, outlier, center, spread for each one. You actually have to compare the values and use phrases greater than, less than, about the same as when you're talking about them. So when you were younger and you were told to compare and contrast two things, a lot of times people miss that point about actually talking about both of them at the same time, and you can't afford to do that here. The center of data set A is greater than the center of data set B, and then you have to give the numbers, or you can work the numbers into the sentence somehow. You have to include statements like that. All right. Again, label and scale all axes, or you won't get credit for doing the plot at all. And since they're fairly time consuming, you don't want to lose credit for that. All right. When you're asked about outliers and you're given the entire data set, you are expected to calculate the outliers. I would use the box plot in your calculator to do that for you. If the question is determine if there are outliers, yes, you need to show your work. If that's not the question, you simply need to know whether there are outliers or not. You can say that you used the 1.5 times IQR rule and the outliers are, and you can get out of your calculator. So make sure that you understand when you might have to show work for that. And then again, don't say average, say mean. Average is a layman's term that doesn't count as an official technical term. Mean is an official technical term. Misusing vocabulary words will lose you points every time. Like I said, range, when we talked about range, we said range is not where you say this data set's lowest value is 3 and its highest value is 7. That's not a range. Range is 7 minus 3 equals 4 in that case. IQR is a single number after you've subtracted Q3 minus Q1. Also, a commonly misused word is skew. So don't say that something is skewed by things. Skew is not a verb in this class. Skew is a description. It's a shape of a data set. It's an adjective. Don't use it as a verb, okay? Pay attention to that vocabulary and review it before every test. All right? Thanks for listening.